All right, we're going to continue our discussion now on the finite state machine. We created a sequence detector that detected the sequence of 110 in our previous lecture videos. We created a Moore machine where a Moore finite state machine, the output of the state machine is dependent on your present state. We're now going to talk about a Mealy state machine, where your output will be dependent on the present state and the input, and it will happen on a state transition. All right, let me, not quite sure why that slide isn't popping up here. Sorry. All right, so in your lecture notes, the Mealy state machine. Sorry for the delay. All right, so it's the same sequence that we're going to detect, right, of 110, right? We just did that with the Moore machine. We're going to create the Mealy machine where we're going to define the Mealy machine as the outputs are dependent on the present state and the input. So remember, the Moore machine, outputs are dependent only on the present state, Mealy dependent on present state and input. And so we're going to draw the Mealy state diagram, which will differ a little from the Moore diagram. We're still going to show all of our states in circles. Right? We're going to show a directed arrow for the transition, but we're going to show the output as well as the input on the arrow, right? With the Moore machine, we showed the output inside each one of these states because the output was dependent on the present state. To remind you, we had our output is named Z, our input is named X, not real important in this slide here. But remember, S0 is our initial, our reset state. We haven't detected any of our sequence. And the first thing we did before when we created the Moore state diagram is we said when we're sitting here in state S0 and our input X is a 1, we want to transition over to state S1. Right. So to the left of the diagonal, the forward slash, these are input values, right? We're creating a state machine that only has one input value. You can create state machines that have multiple bit inputs. All right, first we want to start out and do our easiest case, single bit of input. Then to the right of the forward slash, we show the output values. So this is Z equals 0. So we're saying here, when we're in state S0 and our input X is a 1, we want to transition to S1 and our output should be a 0 on that transition. Right. So we can call S0 do not have a 1, reset state, right? Meaning we haven't recognized that first 1 in the sequence. Right. Now, we want to figure out then what is our state transition when we're in S1, right? So we call S0, I've got the names here of what I'm calling it, no 1, or the initial state. S1, that state we recognize, we've seen 1, 1 so far, so got a 1. In S2, we're going to transition to S2. So when we're sitting here in state S1 and we've seen the first 1 in this sequence, then we want to see the next 1. So when when X is a 1, we're in state S1, we're going to transition to state S2. On that state transition, our output will be a 0. So we're saying when we're in state S1 and our input X is a 1, our output Z is a 0. Right. So now we have 3 states, and state S2 is the state where we're recognizing the sequence 1, 1. This looks just like our Moore state machine so far, except we're showing the output on these transition arrows. Otherwise, we're going through the same sequence. Right. So let's take a look now at what happens when we're in S2. So when we're in S2, the next thing we want to see is a 0. We've already seen the 1, 1, and we want to see the 0. So here we say when we're in S2 and our input X is a 0, here's our input X is a 0. Our output Z should be a 1, right? Because the Mealy machine is dependent on the present state. The present state is, we've already seen 1, 1. So when we've already seen 1, 1, and then the input is a 0, now we've seen 1, 1, 0, go ahead and set the output equal to 1 on that state transition. All right. And then we're just transitioning back to this S0 state based on this last input, right? This last input is a 0. And we'd say, we've seen our full sequence. All right, we received this. We want to go back to the state S0 and wait for the next sequence of 110, right? Simply because this sequence ends with the 0, we know that the 0 couldn't be the start of a new sequence. This 10 couldn't be the start of a new sequence 110. So we transition back to S0. The Mealy machine is a little more complex, right, on these state transitions, but it usually results in a smaller state machine. And it turns out then, right, we only need these 3 states. With the Moore machine, we had 1 more state. So you can think of the Moore machine sometimes as more states. We go through the same thing we did before with the Moore machine. Now that we know how many states we need, this is the maximum number of states that we need, we go ahead and we account for the other possible inputs. Right? So when we were in state S0, we'd already accounted for what happens when our input is a 1. We need to account for what happens when our input is a 0. So when we're in S0, we haven't seen our first 1 yet. If our input's a 0, we want to stay in this state, and our output Z will be a 0. Right. We'll do the same thing then with S1. When we're in S1, we've already seen our first 1. When our input is a 0, well, then we've seen a 1, 0, and we say, do we have a state for a 1, 0? No. Do we have a state for a 0? No. So we're going to transition back to S0 because we need to start looking for that sequence all over again. And our output Z is a 0 then because we haven't seen the sequence that we want. Finally, now we'll determine then what to do when we're in S2 and our input is a 1. Right, so in S2, when we get a 1 input, we're going to stay in the got 1, 1 state because we'll have a string that's 1, 1, 1, 3 1s. And we don't have a state for 3 1s. But just like we did with the Moore machine, if we start peeling off the 1 to the left and look at the next 2 1s, we do have a state for got 1, 1. So we'll sit here saying we've recognized the first 2 1s of our sequence. Remember, we're allowing overlapping sequences. We don't have to start over. And now our state diagram is complete, right? We've accounted for what to do in each state where we have our 2 different possible values of X, our inputs, right? We've accounted for all of our outputs. What we do next is the same thing we did with the Moore state machine. We go ahead and create the state table. So our Mealy state table looks very similar to the Moore, right? We have 3 states, right? So we'll list all 3 states here, S0, S1, and S2. We need at least 2 bits to count 3 states. So that's number of states determines the number of bits we need. So if we have 2 bits, we know we can count the number 0, 0, 0, 1, 1, 0, and 1, 1, 4 possible combinations. So these question marks in this table indicate that we have an unused state, 1, 1. Here are 2 flip-flops that we need. So we need 1 flip-flop to represent one of the state bits, another flip-flop to represent the other state bit. These are our present state inputs, so these are our possible input combinations. Here's our other input X. We have 3 inputs to this state machine, Q1, Q0, and X. All right, so we have these 8 unique binary combinations. All right. So let's start filling in then the state diagram the state table based on our state diagram. All right, let's see. Sorry, I skipped ahead. All right, double click, got me into trouble. All right, so when we were in state S0 and our input X was a 0, we said our next state was S0, right? And we represent state S0 with a 0, 0. And on that state transition, right, we said our output was a 0. So there's where we get the value of Z. If you go back and look at that state diagram, right, which hopefully you're taking notes on pencil and paper or writing tablet, whatever, you're writing these notes down and you have a copy of that state diagram in front of you. Right. So when we're in state S0 and our input X was a 1, we said the next state is S1. Right, so 0, 1 represents the next state. and our output Z was a 0. So we'll go through now. So now we fill in, then when we're in state S1, our input X was a 0. We said we go back to state S0. So here the 0, 0 represents state S0. Our output Z was a 0. When we're in state S1, our input X is a 1. We said the next state is S2. 1, 0 represents state S2. Our output Z was a 0 on that transition. So now let's go through and determine state S2. When we're in state S2 and our input X was a 0, we transition to state S0, right? But we have recognized that sequence of 1, 1, 0. So our output Z was a 1 in that state diagram. The 0, 0 here comes to represent state S0. When we're in state S2 and our input X was a 1, we said we stayed at state S2. So our next state is state S2. 1, 0 represents state S2. And the output Z was a 0. All right. Now, what to do with the unused states? Right? We have two choices. We can treat the state transition as a don't care, or we can force the state transition to the initial state. So what we're going to do is we're going to force the state transition to the initial state as 0 from the unused states. Technically, we should control our hardware in a way that we never reach these unused states. But just in case there's a glitch and we do, what we're going to say is if for some reason our state machine happens to have a value of 1, 1 on the flip-flops in the present state, we want the next state to be S0. And so we've got S0 here in the output, right? 0, 0 represents S0. And of course the output Z should be a 0 in that case because we haven't recognized our sequence. And this then concludes filling in our state table. We're going to do the same things that we did with the Moore machine. We're going to then determine the next state equations for Q1 plus, Q0 plus, and for Z. Of course, Z will not depend on the type of flip-flops we use. Q1 plus and Q0 plus, the equations that we create will depend on the type of flip-flop, whether we use a D flip-flop, a JK, or a T. But our Z output will be fairly easy to recognize, to develop. Right, we've only got 1, 1 for the Z. All right, so let's go ahead and do that. All right, we're going to use a D flip-flop in this example. And we know that our equation or our excitation table for D is simply D is equal to Q next. All right. So if we want to determine what the inputs to flip-flops D1 and D0 should be, they're going to be the same. The inputs to flip-flop D1 should be the same as Q1 plus. So to come up with the equation here for Q1 plus, I'm saying that D1 is equal to Q1 plus. I'm taking this output, mapping it to this K-map where our inputs to the K-map and our inputs to the state machine are Q1, Q0, and X. Right? Solving that equation for these two ones here. Right? And instead of solving for the ones, the note says you could solve for product of sums form. Either form works. We'll do the same thing for D0. We take the column of Q0 plus. D0 is going to be equal to Q0 plus. I'm mapping then these outputs. We only have 1, 1. So I really didn't even need to do a K-map for this because we could have just solved for the 1 without a K-map because we can see that that's min-term 1. So that's Q1 not, Q0 not, and it with X. Right? There's our equation for D0. Finally, our equation for Z. Z is dependent on Q1, Q0, and X, right? With the Moore machine, we were only dependent on the present state, which was Q1 and Q0. With the Mealy machine, we're dependent on the present state and the input. So we'll take this, like I said, I've thrown this into a K-map, but we don't have to throw it into a K-map if we want to solve for the ones. We just have the 1, 1. Z then is a 1 here when our inputs are decimal 4 or binary 1, 0, 0. So our min-term is Q1, Q0 not, X not. That's our solution for Z. All right. And so we could draw that circuit back out. I don't have a picture of the circuit drawing here, right? You're going to need flip-flops, gates. So you could draw that out based on the same way we drew out the circuits for our Moore state machine. What we'll do in the next lecture is we are going to take a look at how to write a Verilog file for this. I suggest you practice as well. We did the D flip-flop here. Good practice would be take this state table, solve it for JK flip-flop, solve it for T flip-flop. So you can practice those techniques. All right, so like I said, the next lecture segment will be on how to write the Verilog for the Mealy state machine. All right, happy practice.